Alright, you're looking at what's called a cylindrical capacitor. So hopefully you've learned about parallel plate capacitors already. But as it turns out, in real life, a more common way to manufacture capacitors is using cylindrical conductors. So we're going to look at how to find values like E field, voltage, and capacitance for a cylindrical capacitor. So first of all, once again, we need to figure out our charge distribution. So we still have plus Q on the inner conductor, minus Q on the outer. So they're going to want to get as close as possible to each other. So they're just going to line up on the faces of the conductor facing the gap. So our charge distribution looks something like this, and our E field lines are going to look something like that. Now to find the specific values for the E field in this gap, we're going to draw a cylindrical Gaussian surface right in the middle of this gap, or not exactly in the middle, but some arbitrary distance between them, such that our cylindrical surface has radius little r and a length, which is not pictured here, length L. And we're also going to have to know the linear charge density lambda of our inner conductor, which we will define to be Q over big L, where big L is the total length of the cylindrical capacitor. So now we write our Gauss's law, Q enclosed over epsilon naught is equal to the integral of E dot dA. So let's start with the left side of the integral, or left side of the Gauss's law. What is Q enclosed? Here it's just lambda times little l, where little l is, again, the length of our cylindrical Gaussian surface. And then on the right side, so this would be the electric flux through our cylindrical surface. But we can do a little trick here by assuming that the cylindrical capacitor is infinitely long, which we can do by as long as the cylinders are very long compared to the separation between them. If we assume that, then there can be no E field pointing up or down the cylinder because we're in the middle of an infinite cylinder. By symmetry, it has to be, there can be no E field pointing up or down the cylinder. So then we can disregard the end caps of the cylinder surface, and we can just look at that rounded face. So that means our A becomes just the outer area of the rounded face of the cylinder. And of course our E field is going to be constant going around that face just by symmetry. So we pull out the E, integral dA, and now that's just the integral of dA for the outside face of a cylinder, which is 2 pi r little l, lambda l over epsilon naught. So now this is going to cancel out, and we find that E is equal to lambda over 2 pi r epsilon naught. Alright, that's a good start, but now we want to find the voltage between the two plates of our capacitor. So just as before, we're going to take V is equal to integral of E dr, and we'll plug in our E inside our integration bounds, going from RA to RB, where RA is just the radius of this inner circle here, and RB is the radius of this circle here. Alright, so then we're going to plug in our E, which is lambda over 2 pi r epsilon naught dr. So then we'll pull out a bunch of coefficients, 2 pi epsilon naught times integral from RA to RB of 1 over r dr. So this is going to come out to lambda over 2 pi epsilon naught times natural log of r from RA to RB. So we end up with lambda over 2 pi epsilon naught times ln RB minus ln RA, which, if you remember your logarithm rules, should be up here. Alright, if you remember your logarithm rules, then this will simplify to lambda over 2 pi epsilon naught ln of RB over RA. And there you have it. there's a formula for the voltage of a cylindrical capacitor. Now, last thing we're going to find is the capacitance C, which is, of course, Q over V. So our Q is just the Q we defined from before. So we have Q, and then V is, of course, down there, lambda over 2 pi epsilon naught times ln of RB over RA. So now lambda we will replace with Q over L. So now these cancel out. We'll reshuffle our fraction a little bit. 2 pi epsilon naught L over ln RB over RA. And there you have it. Cylindrical capacitor.